Code can quickly become a tangled mess, hard to read, harder to change. Early procedural code worked for small scripts, but as software grew, it became fragile and unpredictable. We needed a better way to manage complexity. Object-oriented programming, or OOP, is that solution. OOP is about building software from small, independent components called objects. Instead of a list of steps, we design interacting entities like building with Lego bricks. This approach brings clarity, flexibility, and maintainability. OOP became the standard because it helps teams manage massive code bases. Languages like Java, C++, Python, and C# use OOP to build everything from apps to financial systems. The core problem OOP solves: complexity never goes away. This guide is for developers who want practical tools, not academic theory. We'll focus on the 4 pillars of OOP, showing how they help you write cleaner, more robust code. Our goal: demystify OOP and help you take control of your codebase. With OOP, software becomes easier to understand, extend, and maintain. It's about making code a pleasure to work on, not a burden. Let's break down the core ideas that make OOP so powerful. Ready? Let's dive in. Think of a class as a blueprint, like an architect's plan for a house. The class defines what an object will be, its properties and behaviors. But the class itself isn't an object, just as a blueprint isn't a house. When you use a class to create something real in your program, that's an object. For example, a car class might define color, model, and year, plus methods like start engine. Each car you create, your red Porsche, my gray Honda, is a separate object, each with its own state. Objects are independent. Starting the engine on one doesn't affect the other. This is the power of classes and objects modeling real-world things as self-contained units. It keeps code organized and intuitive. In practice, you define a class once, then create as many objects as you need. Each object is unique, but all share the same structure and behaviors. This makes your code flexible and reusable. OOP lets you build complex systems from simple, understandable parts. You can add new types of cars or any object without rewriting everything. That's the foundation of OOP: blueprints, classes, and real things, objects. It's how we bring order to code. Next, let's see how we keep these objects safe and organized. The first pillar is encapsulation, bundling data and methods inside an object and hiding the messy details. Think of a car: you use the steering wheel and pedals but don't see the engine's complexity. In code, we make properties private and expose only what's needed through public methods. This protects the object's state and enforces rules like preventing a bank account from going negative. Encapsulation makes objects reliable and self-contained. The second pillar is inheritance. Inheritance lets you create new classes based on existing ones. For example, a vehicle class might have speed and accelerate. Car and motorcycle inherit these, then add their own features. This promotes code reuse and organization. You write common logic once, then extend it for specific needs. Inheritance helps you build hierarchies general to specific, without repeating code. Together, encapsulation and inheritance make code safer and more maintainable. They let you build on solid foundations, adding new features without breaking old ones. These principles are essential for managing growing code bases. They keep your code clean, modular, and easy to understand. Next, let's explore how OOP handles variety and complexity. That's where polymorphism and abstraction come in. The third pillar, polymorphism, means many forms. It lets you treat different objects as if they're the same type, as long as they share a common parent. For example, you can loop through a list of vehicle objects, cars, trucks, motorcycles, and call start engine on each. The right method runs for each object, even if they're different under the hood. This makes code flexible and easy to extend. Add a new vehicle type, and your existing code still works. Polymorphism decouples logic from specific types. The fourth pillar is abstraction. Abstraction hides complex details, showing only what's essential. You use a user service without knowing how it talks to the database. Abstract classes and interfaces define what must be done, not how. This reduces cognitive load and keeps code focused. Abstraction and encapsulation work together. One hides data, the other hides complexity. These pillars let you build systems that are powerful yet simple to use. They help teams work in parallel, each focusing on their part. OOP's pillars are the secret to managing complexity at scale. Let's see why this matters in real projects. OOP's 4 pillars aren't just theory, they're survival tools for real-world software. Encapsulation creates boundaries so bugs stay contained and are easier to fix. Inheritance and polymorphism make code flexible and ready for change. Add new features like supporting spreadsheets without rewriting core logic. Abstraction lets teams work independently, focusing on what matters for their part of the system. No one needs to understand every detail, just the interfaces they use. This separation of concerns is key for large teams and big projects. OOP helps you build robust, adaptable systems that grow with your needs. Clean, object-oriented code is easier to read, debug, and extend. It's an investment that pays off as your project evolves. Adopting OOP is about professionalism and future-proofing your work. It empowers teams to build better software, faster. Embrace these principles as practical tools, not dogma. Start applying them and you'll see the difference in your code base. OOP turns chaos into order, making software a joy to build and maintain. That's the real power of object-oriented programming. Thanks for watching. Now go write some great code.